So as we continue, so for our problem, a section of highway is known to have a free flow speed of 55 mile per hour and a capacity of 3,300 vehicle per hour. In a given hour, 2,100 vehicles were counted at specified point along this highway section. If the linear speed density relationship applies, as shown in the equation a while ago, what would you estimate the space mean speed of this 2,100 vehicles to be? So to start with, we have to compute first for our jam density from the equation wherein we have a maximum flow capacity is equal to case of J times use of F all over 4. So make use of this so that we can compute for our maximum jam density, which is case of J. And if we try to substitute the value, we have to take note that our maximum capacity is 3,300. Then our use of F, which is equivalent to 55. That is our free flow speed use of F. So we get a value of 240 vehicle per mile. So therefore, if we're going to use the equation introduced previously, which is Q is equal to case of J times U minus use squared all over use of F. So we simply have to solve this one. If you're going to have the value, if you're going to simplify this one, we can have this equation. So having this equation, we are going to solve now for our U. So for the speed, we simply have to substitute our case of J, which is our jam density. We computed that as 240. Then our U is unknown, of course. Our Q is, for this one, we are going to have, we're given with 2,100. This is our 2,100 vehicles in an hour. So we simply have the value now for our Q. So that will give us, if we try to simplify this one, it will give us a value of 44.08 mile per hour or 10.92 mile per hour. So both of this speed are feasible. So we can make the speed, because for this one, this is quadratic, so which means we have two values for U, meaning we have two values for our speed. So both of the speed are feasible. So we move on to models of traffic flow. So with the basic relationship that was established a while ago among traffic flow, speed, and density, we now formalized we now focus on the microscopic view of traffic flow. So that is, instead of simply modeling the number of vehicles passing at specified point on a highway, in some interval, there is considerable analytic value in modeling the time between the arrival of successive vehicles. So actually, the time arrival in between vehicles, in between successive vehicle, is what we call time headway. So time headway actually is the time between the arrival of successive vehicle. So the most simplistic approach to vehicle arrival modeling is we have to assume that all vehicles are equally or uniformly speed, so that we can have that is how we're going to have an assumption if we try to model the vehicle arrival. So vehicle arrival, the time in between vehicle arrival, is what we call time headway. So under this assumption, wherein we assume that all vehicles are uniformly speed, if the traffic flow is 360 vehicle per hour, the number of vehicles arriving in any 5-minute time interval is 30, and the headway between all vehicles is 10 seconds. So since our H here is equivalent to 3,600 per Q. So, however, actually in actual observation, it showed that some of the uniformity of traffic flow is not always realistic because some 5-minute interval are likely to have more or less traffic flow than the 5-minute interval. So, this representation now of vehicle arrival goes beyond the deterministic uniform assumption, which is often warranted. So for Poisson model, we have here a model which is which account for the non-uniformity of flow that is derived by assuming that the pattern of vehicle arrivals correspond to some random process. So the problem becomes selecting a probability distribution that is reasonable representation of observed traffic arrival patterns. So which means that this Poisson model is a model which represents to describe the non-uniformity of flow of the that was derived by assuming that the pattern of the vehicle arrival correspond to some random process. So for Poisson distribution, we have here an equation. So this piece of n, p which is actually probability, p parenthesis n, this is p which is a function of n. This is now the probability of having n vehicle arrival in time t. That will be equivalent to lambda, which average vehicle flow or arrival rate in which per unit time times t, which is raised to n, multiplied to raised to negative lambda t all over n factorial. So our t here is the duration of the time interval over which vehicle are counted. Our lambda is the average vehicle flow or arrival rate in vehicles per unit time. So for our example, we have here an observer counts 360 vehicle per hour at a specific highway location, assuming that the arrival of the vehicle at this highway location is Poisson distributed. Estimate the probabilities of having 0, 1, 2, 3, 4, and 5 for more vehicles arriving over a 20-second time interval. So for this one, our average arrival rate lambda is actually 360 vehicle per hour, or that is 0.1 vehicles per second. So if we're going to have, so therefore our lambda is 360 vehicle per hour, or if we're going to have this in vehicle per second, so therefore we have 360, so vehicle per hour. So if we're going to have here, this is divide all throughout by 60 because 1 hour is, or they can have here, you can have here times 1 hour is 60 seconds. So this will result to, so this would result to, this is actually minute. So 1 hour is 60 minutes. So this will result to 6 vehicle per minute. So if we're going to have here in seconds, so times 1 minute is 60 seconds. So this would result to 0.1 vehicle per second. So that is the main reason why we have, that is also equivalent to 0.1 vehicle per second. And our t here is 20, our t is 20 second, because this is the time arrival, 20 second. And our, so we're going to solve for the probabilities for having a 0 vehicle, having 1 vehicle that will arrive, having 2 vehicle that will arrive, 3 vehicle that will arrive, and 4 vehicle that will arrive. So, and of course, what will be the probability that there will be 5 or more vehicles that will arrive with an interval of 20 seconds. 0 vehicle meaning to say probability that there will be no vehicle that may arrive. So which means that we're going to have these equations. So we simply have to identify this one is no vehicles that may arrive. So meaning to say our n is 0. So have a probability that n is 0, no vehicles that may arrive. So substitute to our equation that we have to our equation, which is our equation actually is p, a function of n is equal to lambda times t raised to n multiplied to e raised to negative lambda times t all over n factorial. So that will be what will be the probability that there will be 0 vehicle, 1 vehicle, 2 vehicle, 3 vehicle, 4 vehicle, or 5 or more vehicle that may arrive having a 20-second time interval. So which means you simply have to substitute. So our lambda here, which is we have computed our average arrival rate, which is, we make use of this, which is 0.1 vehicle per second. So substitute times t. Our t is 20 second raised to n. This is 0 since no vehicle may arrive. E raised to lambda times t all over n factorial. So we got a result of 0.135. So if there will be 1 vehicle, 2 vehicle, 3 and 4, so these are the result. So you simply have to substitute the value. What changes here? The only change here, of course, in our formula, you are going to use this equation. What will have the change that will occur is on the value for n. So there will be 1, 2, 3, and 4. So this is the result, 0.27 for 1 arrival vehicle, 2 for 0.27 for 2 arrival vehicle, and for 3 arrival 0.18, and for arrival we have 0.09 vehicles. So therefore, if we are going to have now, what will be the probability that there will be 5 or more vehicle that may arrive? So meaning to say, if there will be 5 or more vehicle that may arrive, so what will be the probability? So our equation will be this one. So P is equal P wherein our n is greater or equal to 5. So meaning to say there will be 5 or more vehicle that may arrive. So this will be the equation, or this is the representation that will be equivalent to, so 1, because if we're going to add all this probability, those are equivalent to 1. So that will be 1 minus P times 1 minus probability wherein n is less than 5. So when n is less than 5, these are the values. So you simply have to substitute that one. So we have computed that one for 0, for 1, for 2, 3, and 4 vehicles arrival. So subtract all those to 1. So we have here 0.053. So this is the probability that there will be 5 or more vehicles that may arrive. So that's how we're going to compute for this, the last probability. So we have here our histogram. This is an histogram. This is a graph showing to us the histogram of the Poisson distribution, wherein our lambda is equal to 0.01, 0.1 rather vehicles per second, and this is now, we have now the corresponding number of vehicles arriving at 20-second time interval. So we have 0, 1, 2, 3, 4, and 5 or more vehicles. So we have now the corresponding probability for the arrival of those vehicles.